everyone. My name is Yazen, and this is Steve. Today we're going to talk about storage and file system optimizations. But before we get started, you may have seen on the schedule it's changed a little bit, so we're going to be talking for about half an hour. And then after us, there's going to be another presentation on porting Openjdk to 32-bit. Okay. So let's get started. So basically what we're going to do is we're going to discuss the file system and storage optimizations that we've done over about the last year. Most of it was kind of low-hanging fruit, and there was some basic, some simple bug fixes that kind of went in there that helped out. So the three projects we're going to be talking about are Ceph, the Linux kernel, and Hadoop file system. And then we're going to discuss some possible future work that we could probably do, and we'll finish up with some Q&A. So the first project is Ceph. Ceph is a distributed storage system. It's written in C++ mostly. And we introduced Ceph at the last Connect in Hong Kong. And we kind of went over like the basic architecture and some things there. And so one of the questions that a lot of people ask and asked before is, does Sef work on ARM64 or ARM64? And the question is, yes, it pretty much just works. It builds, there's some packages and some distros. But of course, you know, with the new architecture, there were some areas for improvement. And so that's kind of what we were focusing on over the last year. The first and probably most obvious improvement that we could do was for CRC32C. So this little snippet here is from perf. It's a little perf report snippet. You could see about 26, this is from a single process. You can see about 26% is spent in the software implemented CRC function. So this is actually from one of the benchmarks that's built into Ceph called Rados Bench. It's doing a write operation for 60 seconds on ButterFS. So some background there is the ARMV architecture has some optional extensions, and one of them is CRC32. So that basically is like a hardware accelerated, you know, operation. So this was added to Ceph. They have a similar thing for x86. And this is actually in Ceph version 9.0. So it's upstream, and it should be in the next release. And I'll hand it over to Steve.
Hi, guys. So Yazen's gone through the CPU analysis of Ceph, and that is one part of the story. Ceph is a storage system. There are more components in play than just the CPU. So decided to take a look at the wider picture and see if we could spot any other things that were quite pertinent for optimization. The system activity report was used because it was simple and it provides a very nice way to get a picture of disk activity, network activity, process, memory, all that sort of thing. And the great thing about SAR is you can synchronize time between nodes, which one does anyway between Ceph, and one can perform comparative analysis and actually view quantitative and qualitative differences in behavior as well from the telemetry gathered. To drill down into block I/O a little bit more, the Linux kernel has got quite an amazing level of instrumentation available in the form of block trace, and we actually used a bit of block trace as well to get really into the disk activity. The initial activity with block trace has not been very extreme or hardcore or anything. It's just been a lot of QA and testing. It will make its way in soon. It's of particular interest to people who are running Ceph with a 64K page size, because it will help in certain circumstances. There's a lot more documentation in the commit log itself. So here's an example of block parse. So this is the counterpart to block trace. Block trace, as I mentioned before, grabs a lot of the block I/O layer information. This is a summary of differences between writes queued with and without the patch I mentioned for the journal. So the pertinent part is in red. So essentially we go down from about 2.2 3-ish gigs down to 600 megs for a similar workload written. So we're doing less work to the disk. This is a good thing. We're making it in line behavior-wise. Spurned on by this behavioral change in page sizes, the upstream themselves advised we check out this so-called buffer list class. And the buffer list is an internal allocator that is used within Ceph. And this has a piece of behavior keyed in via page size again. The buffer list itself will concatenate in size a page at a time. And again, this is a slight behavioral difference for 4K and 64K pages. It turns out running the metadata server, one actually gets memory spikes when running the metadata server on mount and things like that. But when running with 64K page size, it's not quite 16, but it's roughly 10 times spike in memory usage due to the way the buffer list works. So this has been fixed again. The patch is, again, it's in master. It's just got to work its way down into a Ceph release. I'll hand back to Yazen to talk about QA.
Yeah, so one of the things we identified that we wanted to check out in our last talk in Hong Kong was Teuthology and the Ceph QA suite. So Teuthology is Ceph's integration validation kind of framework. So you get past the basic unit tests running on a single machine, and you start to have like an actual cluster of machines doing some kind of real world type tests. And so that Teuthology is the framework, and the Ceph QA suite is actually the suite of test cases. So we thought it was a good idea to kind of check this out on ARMv8 hardware. So we have some machines in the Austin Colo lab. We had a few APM Mustangs and a few AMD Seattles. Our Teuthology cluster kind of has been growing and shrinking depending on what resources are available. We've had from 4 to 9 machines in the main cluster, and then we added the HP Moonshot towards the end of it to add another 18 Applied Micro Mustangs to the cluster. So the Ceph QA suite actually has a lot of tests. It has about 5,500 tests. And the way they're actually defined is they're kind of grouped into suites and subsuites based on the different components in Ceph. So have like Rados is like a suite of tests for Rados, and then for the Ceph file system, et cetera. And then there's further subsuites that kind of have maybe a theme to them. So you'll have a subsuite of like basic tests and basic functionality and or verifying the functionality. And then you may have another subsuite in that same component that does maybe stressing and thrashing, and that might cover more corner cases and a lot more things there. So the tests are kind of defined in these YAML fragments, and then when you kind of when you schedule a suite or a subsuite to run, the framework will basically build the test cases out of these fragments, concatenate them, and basically build the actual test definitions from them. So when you actually do that for all the subsuites, you get a lot of test cases. There's not that many basic and verify kind of test cases, so we kind of focused on that first. Mostly for pretty much all the components, the basic and the verify subsuites are passing on AR64. So the basic functionality is there. They seem to be working fine. When you get into the thrashing and the stressing, there's some things that it's kind of a mixed bag of passes and fails. So as an example, the bufferless patch that Steve wrote up, when I applied that and we ran the tests on that, actually a few more test cases were passing, especially in the Ceph file system and the metadata server test cases. So it seems like that relieved some of the I/O pressure and allowed more test cases to pass. And that kind of brings up another point. The machines we have in this cluster, that we had in the cluster, are machines in the colo, so they weren't designed to be used for validation so much as enablement. So if you haven't heard about the colo, you can reserve a machine, ARMv8 machine. It comes with a traditional hard drive with maybe 500 gigs and quite a bit of memory. And they're all connected and with 1 gig Ethernet. So that's the kind of machines we were using. So relieving some I/O pressure kind of helped there. So moving on from Ceph, the Linux kernel, one of the things that was upstreamed about a year ago now was the CRC32 module. So both CRC32 and CRC32C are used, and they're implemented in version 3.19. It's a pretty simple module, but it's used by different components. So ButterFS seems to use CRC quite a bit, CRC32, and some of the Ceph code also does. So it was kind of a simple module. It enabled one of the optional instructions, but it seems to have helped a lot. And this was kind of done in the last year because before like the last year, there wasn't any ARMv hardware that was public that had these extensions. So when this hardware started to come out and we were able to use them, then these things started to get proven and tested. Okay, and I'll hand it back to Steve.
Hi. So one other thing we were testing at the time was a set of patches for AH64K probes and U probes. These are being worked on, but the patches are on the mailing lists publicly, so we decided to actually use them, and it's the best way of actually testing them. So K-probes is a mechanism to place, for want of a better expression, breakpoints in the kernel in such a way one can gather telemetry. So for instance, for a particular function, you can place a K-probe in the middle of it and ascertain what certain variables are via the registers. There are certain limitations. You can't do everything with K-probes, but it's a very useful mechanism. K-probes itself is leveraged by a mechanism called U-probes, and U-probes basically allows one to place these breakpoints, for want of a better expression, or probe points in any sort of system library or executable that's loaded by the Linux kernel. It keys off the file. So one can do quite powerful things. For instance, they could say, okay, place a probe in the C library, and anything that's using that particular inode of C library where the U probe is placed is probable. So this allows one to gather quite a lot of telemetry. Now, Linux perf is quite good at filtering things and analyzing things, and one can actually use Linux perf in combination with K-probes and U-probes. So for instance, we may want to restrict our attention to Ceph. So one particular piece of analysis performed was to take a look at memcopy size utilization. So everyone's favorite function, memcopy, takes a destination, a source, and a number of bytes to copy over. Sometimes memcopying size 1, for instance, is particularly wasteful endeavor to go on. So decided to have a look and try to analyze where memcopies of size 1 were occurring. And one can basically place a U probe in the C library for the memcopy, and then they can use perf to gather information restricted to Ceph. We can then use these flame graphs to visualize the perf data, and this gives, it's quite horrible to read, but the perf flame graphs themselves are interactive. One can explore the frames and get a good behavioral idea where certain code characteristics are coming from. So it's quite a convenient way of analyzing an application. And the great thing about the U probes is we don't recompile, we don't do anything. We run the production code and we probe it with the kernel. And we can use quite a lot of machinery to analyze this data. So, hand back to Yazen for Hadoop.
Yeah, so Hadoop, there's going to be more in the Hadoop session, which I think is tomorrow, right, during leg day. So check that out if you want more information on Hadoop. In terms of optimization, similar to Ceph in the kernel, there's CRC32 was coded up by Ed Neville to run in the Hadoop native library, and this is a link to the Jira issue. So Ed actually, his implementation here is a pipelined implementation. So in the micro benchmarks, he's actually getting 11 times speed up, which is great compared to the software implementation. And this is going to make it in the Hadoop 2.8 release. So the pipelined speed up basically is rather than going through the CRC buffer and running the CRC instruction on a single piece of the buffer at a time, which is what we're doing in Ceph in the Linux kernel. That gets you about a 4.5 times speed up. The pipeline implementation is, you do more in parallel. So you can run, for example, in this example, you might run 3 CRC operations at one time, and you're going to get not necessarily a 3 times speed up, but there's some overhead there. But it's quite a bit more. All right, and Steve, you want to talk about this?
Okay, so we've talked about some of the performance work we've done with Ceph. I've quickly mentioned we used the system activity report. This is the system activity report of the CPU for an RBD bench write. The pertinent part of this graph is the large blue area at the top, which is the idle CPU. We're hardly touching the CPU with this benchmark. We are basically saturated on, for this particular case, disk. We have to consider networking as well. Yesterday, Nashiket gave quite a good keynote demo when he showed the effects of running with 1 gig versus 10 gig for a H2O cluster and how 1 gig gigabit limited the performance scaling. Again, for Ceph is a network distributed storage system. It's going to need network, it's going to need disk. So for future work in Ceph, we essentially need higher spec hardware. So we've done all we can with the dev boards we've got, but as higher spec disks, higher spec networking becomes more commonly available in hardware, AH64 hardware, some of this work will need to be repeated again to see if anything's changed. The CPU profiling information will very likely change when running under higher stress workloads because of having higher spec hardware there. So yeah, for future work, need to do it again on higher spec hardware is one particular item.
So another area of future work is basically looking at libraries and some things like that. So as we're getting higher and higher in the stack, and different projects are going to become less the focus directly and more kind of the spotlight that we use to find opportunities in underlying software. Ceph and Hadoop, they have native, or Ceph is C++, and Hadoop has a native component. So we're kind of, there's still some things we can do directly in those projects. But as we get into other projects, especially in Leg, we're probably going to want to spend more time looking at libraries. As an example for Ceph, these are some components that are in Ceph that we could probably look at further. One is tcmalloc, that's the thread caching malloc, and that's in the Google Perf tools. So that's one of the things that people were asking, is this available on AR64, and it has been for quite a bit. It's been enabled, but the question is there more optimization? Can we make it better rather than just enabling it? Another example is Boost, the Boost C++ libraries. And this will probably benefit more than just Ceph in the future. A lot of projects seem to use these libraries. RocksDB is another example we could look at for Ceph. So we can look at them further. And basically, kind of the idea we've been getting through over the last year is we need to get past kind of enablement and get more into, making things run really, really well, and try to find any opportunities that we can. And as Steve was saying, when we get probably more hardware, more resources to stress, the cores and the software stack together, these things may become more apparent as areas of focus that we can investigate. One last thing that is something we could try to look at is investigating the pipeline CRC on other projects besides Hadoop. So Ed's work is really good for Hadoop with the pipelined implementation. This idea, though, seems like I think it was kind of already in Hadoop for x86. So it kind of fit with their software model. It may or may not benefit Ceph and the kernel, depending on maybe the size of the buffers and the way it's used, because there is quite a bit of overhead. It's not just doing CRC in parallel, but then there's some extra math to kind of merge all that together. So it may or may not benefit, but it is something we can check out in the future. And so thanks for your attention, and if you have any questions, please let us know.
And please use these microphones.
So two things. One thing is that the toolchain guys, especially Bernie Ogden, was supposed to be looking at lockless mallocs. So you might want to talk to them. Bernard Ogden, from the toolchain group.
Oh, yeah, okay.
Yeah, so that's one number one. And the K-props and U-props, did they just work, TM, in your experience?
They're still in progress
Yeah,
on
but
the list.
the stuff that you've got, did it just work? Was there some, have you experienced some issues?
They just work as they are. Because, well, U-probes is okay. K-probes has one slight issue with conditional execution as it stands. Okay. But I can talk to you about that. Okay, well, you know what Yazen and I look like, so please do find us afterwards, and we can talk more as well offline. Thank you for your attention, guys.
Hello? Sorry? Hello? There we go, it is. Okay. Okay, then I'll get started. Hi, I'm Joseph Joyce. I've been an intern at Linaro for the past 13 weeks, working on producing a native version of Openjdk for 32-bit ARM processors, so mainly targeting ARM7, but hopefully ARM6 as well. It's not quite working for ARM6 yet, but it hopefully will be soon. Okay, so Openjdk is an open source implementation of Java. It contains kind of all the bits you need to make Java work, the libraries and implementation, Corba, etc. The virtual machine is called Hotspot. And it's Hotspot that needs actually modifying to make it work on different processor architectures. So inside Hotspot, you have 2 interpreters and 2 compilers. Now, the first of the interpreters up there, 0, is a pure C++ interpreter. So it was already working on ARM processors, but doesn't deliver as good performance as the second of the 2 interpreters, the template interpreter, which actually has platform-specific code. So I've been working on making a template interpreter version for ARM32. The 2 compilers in there, the C1 and the C2 compilers, are otherwise known as the client and server compilers. The C1 compiler is faster but generates worse code, and the C2 compiler generates better code. They normally operate in tiered fashion, so you've got the interpreter starts, and then when this code is frequently executed, you then get it C1 compiled and then C2 compiled, if they're there. However, the interpreter can do it all. You don't need the compilers to make it work. So the compilers have not been implemented, but the interpreter has. Okay, so what's the existing kind of field for Java Openjdk on ARM? Well, for the 64-bit ARM8 processor, there's a full implementation of the template interpreter, the C1, the C2 compilers for Openjdk 7, 8, and 9. In 9, it's been put into the main source tree rather than being maintained separately. For 32-bit ARM processors, the 0 interpreter was working for 7, 8, and 9. ICE-T, which is a kind of fork of Openjdk 7, contains 2 separate things that aren't based on the normal interpreter compiler stack, but are instead based on the 0 interpreter, the ARM microjit, and the ASM interpreter. The microjit's, as it sounds, an actual compiler, and the interpreter's been a specially handwritten one and isn't related to the template interpreter, but because they're based on the 0 interpreter, it means that keeping them up to date with the latest developments is somewhat harder, because they have lots of specific information in them, offsets of things and structures, and whenever the zero interpreter changes, they then need to be brought up to date. So they are currently only on ICT 7 and haven't been updated. I don't know if they will be, but they haven't at the moment. So when developing this port, essentially, as there is a 64-bit ARM one working already in its, well, JDK 9, which is what we're targeting, it's in the main tree, it made sense really to start with that. So the approach essentially has been to take that code and then just modify the bits that are necessary. Indeed, the 32-bit ARM 7 cores have many of kind of the same instructions that have the same arguments, same kind of addressing modes, and so actually the work to change them is not too hard. So the encodings of them, however, are different. So really it started as development to rewrite the assembler so that the instructions get changed to ARM 7 instructions, and essentially just iterate and try to keep the thing compiling until it works, essentially. So basically, a lot of the internals of it are very similar. There's been some small changes to the frame layout in a kind of attempt in vain to get GDB to generate stack traces. I changed some of the layout of the frame. It didn't generate stack traces. It works with the new frame layout, but it could be reverted back to the old one if it makes life easier in any future developments. The largest challenge is probably the reduction in the number of registers available. Trying to take code that was written with roughly 32 registers available and converting them down to approximately 16 was a bit of a challenge at times. I think one of the main difficulties that came about was the 64-bit code assumes that there's a separate Java expression stack pointer to actually the stack pointer. And early on, it seemed like a really good idea to roll the two into the one because the stack pointer just points to the end of the frame whilst the expression stack pointer moves. And so you could combine them. However, that then led to quite a lot of things to change to do with calling in out of C code and handling exceptions and restoring things. And I think maybe if there was any future developments, looking at the C2 compiler, it doesn't always save the frame pointer, which is what I currently use for stack traces in the code. So it might be something of an issue, but I've not looked too deeply into that, so I can't really actually comment on whether or not that would be much of a problem. Okay. So just to give a kind of example of some of the features of the interpreter, this is the template, well, the code that's generated for an integer shift left in Java. So as it's stack-based, you can see that it pops the two arguments, the value and the shift, does the thing, and then at the end there dispatches the next byte code. Just a couple of things to note is that the two pops, the interpreter actually caches the top of stack value in the registers R0 or R1 or D0 and D1. So it doesn't actually always push and pop. So there's kind of two entry points. If you enter with an integer, you go into just pop R1 to pop the second one, whereas otherwise you're going to pop R0. And then at the end, the value's left in R0. And will need to be pushed if you're going to an instruction that doesn't accept an integer argument. I should maybe also mention that point when I said about using registers D0, D1. It is a hard float-only thing. It requires floating point support. Sorry.
So is this there's the code that you've made for ARM 7?
So this is ARM 7, yes.
Yeah, okay. That's V7.
Sorry, yes, V7, yes.
There is one thing we can talk about later. You could have just single pop taking both registers. There's a difference between the edges from the
Okay, that would be good. Yes. Also, I should say, if there are any questions, please, just ask them. Yes, and yes, sorry. It's hard float only. It also supports, in theory, soft FP, but actually requires floating point support at the moment. Okay, so where is it at? Well, it more or less works now, and it with ARM v7, it's working. I think it's very, very close. Kind of, I just need to compile it for ARM v6, I think, to have it working for ARM v6 as well. But it's at the moment I haven't run it on ARM v6. It's been tested with a range of programs. It runs Eclipse and JEdit and Javac. As I said, it's a hard float at the moment, but there's soft FP support for calling in a soft floating point fashion, but still using soft FP and still using floating point instructions. But that, and the choice of that is determined on when you compile, how you compile OpenJDK. That's the calling convention you'd have to use for JNI libraries. There's some known bugs. There's some bits that I need to still develop to actually make it properly, fully correct. And there's a bug, for example, it'll occasionally segfault on startup, which is a serious issue that would need to be fixed for going into production. But, you know, it's, yeah.
Do you have access to the Java test suite?
Yes, well, JTReg, is that, sorry, what you mean, yeah?
There is a Java TCK, is a test suite, instead of the original Sun tests.
Okay.
Every VM has to pass. Do you have access to it? Because it's not publicly available.
I've not done that. Sorry, oh, yes.
Yes, we have access to Linaro, but no, it doesn't run.
Okay, yeah. Because that's the obvious thing to run, right?
Yes.
Yeah.
But it's in time.
Yeah, it's, it does need a lot of testing still. So I just thought I'd give a quick demo just to, fingers crossed it'll work, but you know, let's see. So if we just change over to here. I've got a little ARM7 quad-core chip board. Thank you, V7, yes, running down there. If I just SSH into it, hopefully this will work. It's not normally this slow. There we go. Okay, so as you can see, it's ARM v7. And, there we go. So it'll take maybe a little bit of a time to start up, but it's just going to run JEdit. I think maybe whilst we're waiting for it to start up, I should mention something that when I was developing, I found that surprised me was that actually when running Java, it's before it even gets to run Hello World, it's 2.5 million bytecodes, which I found quite surprising when developing, but there we go. It is working, and it's not the fastest performing thing, as you can see if we go up here and have a look along the menus. It's a bit laggy, but essentially more or less functional. If we just go back to the demo, I'm presenting. Okay, so as you saw, it's the speed of it's not excellent, but I have done some benchmarks just to sort of indicate the performance that you might get out of it. So if we have a look here now, the first one there, the blue, is the Oracle proprietary JDK8 implementation for ARM v6. And that features a C1 compiler, so you get results from EEBMC grinder bench, which is just the benchmark I picked to run, of about, the scores are about 10 times faster. And then going down, you can see the microjit for JDK7, which is also a compiled code. And then after that, you get down to the hand-coded ASM interpreter, which has interleaved dispatch as well as execution of the bytecodes, and because it's been written in that way rather than, as you saw earlier with the template, just loading arguments, doing the bytecode, and then dispatching the next, you'll get better performance. And then going down, then the template interpreter, which is the development that I've been working on, and then at the bottom, 0. So although it doesn't look like a huge gap, if we go on to the next slide, just for a comparison, I've run on this board the template interpreter for JDK9 versus the 0 of JDK8, and you see an 80% improvement in the score that it's given, whereas for running on an x86 desktop machine, you only see a 30% improvement. So realistically, it's probably about as good as it's going to get. There's maybe some improvements still to be made. It does intrinsics mathematics methods at the moment, for example, exponentials and sines and cosines. There's other things. The ARM64 version contains support for doing CRCs and AES things using actual intrinsic code and neon acceleration, but it could be possible to implement those on ARM v7 and ARM v6, but it's, yeah, at the moment it doesn't. Right. So yes, if you are interested in having a look at the code, currently it's just hosted in several repositories in my Bitbucket account. Hopefully it will be moving to an ICT or OpenJDK repository at some point in the future. There's no time frame for that at the moment. If you go on to openjdk.linaro.org, there's a short bit describing it and giving some binaries to download for Trusty and Vivid for ARM v7. And also some guidance about building it, because you have to use, when configuring, you need to specify the target and the version. You need to tell it to build the core version variant. Okay, so what is left to be done? Well, the code needs a cleanup, really, because it was based on the 64-bit version and just sort of the minimal change needed. There's lots of files and things left around from the C1 and C2 compilers that just aren't used, as well as dead code in the existing files that are required, so that needs a cleanup. It needs a lot more testing, as I mentioned earlier, and actually properly putting through test suites and having JT-reg and things running on it. It's hopefully moving to an ICT repository, like I said, but there's no time for that, no time frame for that. And also, 64-bit atomic loads and stores are a bit of an issue because at the moment it just uses a load store double instruction to load 64-bit values. However, the Java spec guarantees that these are atomic, when the architecture spec doesn't say that they'll be atomic, so you might get words or bytes mixed up from two separate writes in a read. That can be solved on ARM7 by using a load and store double exclusive, but it doesn't do this at the moment. Yes, for ARM6 it's a bit more of a problem because there isn't, there isn't on the load store double exclusive. There might be on v6k, but I can't remember. So really, it will only work on a single core machine properly. I haven't really considered what to do on a dual core machine, but that development still needs to be done, but it should be complete fairly soon. If I just move on. So yes, really that's kind of the progress. If there's any questions, I'm happy to answer them, or you can find me afterwards or whatever.
So you said that you would move that to the ICT repository. So why not OpenJDK proper?
It might be.
We'll try and move it to OpenJDK proper. We will try and move it to OpenJDK proper. So I will post it as a project in OpenJDK. If it's accepted, we put it in OpenJDK. If they don't accept it, well, we put it in this.
And next question is, do you follow the weekly snapshots for OpenJDK 9? Do you merge them, or do you build with a fixed version?
It's not yet been merged up to the latest version. That needs to be done. I'm going to try and get it to a state where I'm happy with it on the current version. I branched it off from the latest development.
Essentially, we have taken a snapshot.
Yeah.
Joseph has done this over a period of 3 months, which is amazing work. So he just took a snapshot of that, beginning and worked on that, and now we have to organize it into a project, get it merged up correctly with the latest.
So there's an
Perhaps go up here as well.
So what about a backport to OpenJDK 8? I know there's an ARM64 JDK 8 repository. Would it be possible to backport to that repository?
Yes, it would. We're not planning that. And the goal for this would be to continue its development. Okay, so the old microjet was based on top of 0, and that had some fundamental limitations to do with the frame structure, which inherently limited its performance. You saw the performance difference between the Oracle proprietary and the microjet. So we're now looking at rebasing on the template interpreter. So once we've done that, then we can have C1 and C2 JITs based on top of that, whereas previously we couldn't do that. So I think that the next stage would be to do the C1 and C2 JIT, rather than, at this stage, backporting the template interpreter, because there's no point in using the template interpreter. You know, it's a great piece of work, but still, it's very, very slow. Okay, so you're better off at the moment using the microJIT rather than the template interpreter. But it's hoped to be a basis to get C1 and C2 as a community project, because yes, we would like other people to get involved. If you want to, Matthias, contribute some code to C1.
Well, I can package it, yeah, sure.
Yes, thank you for coming. And if you do have any questions you want to ask me, I'll be around for a while and you'll just grab me later. Okay, thanks.